We walked on the moon 45 years ago, so it should only be reasonable that a human with sufficient nutrients and an active schedule can live in outer space for over 2 years. Humans have long been dazzled by Mars since they first saw it. Today, its human exploration seems to be the next frontier, a far frontier, as the longest that any human has spent away from home is only 440 days. Due to its consistency on Earth, we take the force of gravity for granted, but variations in the force of gravity can take a serious toll on the human body. You can never escape the force of gravity. Objects orbiting the Earth still feel a relatively large pull from the Earth's gravitational field. However, for a shuttle trip to Mars, the Earth's pull of gravity decreases to nearly negligible amounts. When leaving Earth, astronauts often coin the term weightless. They are experiencing microgravity. What happens to gravity when people and objects go into orbit? How do you get this microgravity? Regardless of what you are doing, you are affected by the action to distance force of gravity. Although you may think you can feel gravity, it is in fact the contact felt with objects as a result of gravity that makes you have the feeling of weight. Today, the scales used to measure one's weight abide by Newton's third law. An applied force will be met by a force of equal magnitude in opposite direction. Assuming you are on a level plane, a scale only measures the normal force that the scale is applying on you. As you aren't sinking into the scale, its normal force is equal in magnitude to the force of gravity. People in the International Space Station or any other vessel orbiting the Earth are constantly falling as a result of Earth's gravitational pull. Both the vessel and the occupants undergo free fall at the same rate. They will never meet as the passenger is constantly chasing after a ground that is running away. In this cat and mouse game, there is no point where the vessel and the passenger come in contact, so no normal force would actually be felt from the vessel walls. This feeling is commonly linked to the term microgravity. This is incorrect as the gravitational force on an object is not even close to zero in the low Earth orbit that the ISS is in, so you can finally lose all of those pesky pounds. Well, kind of. What do we know about the effects of microgravity on the muscular and skeletal system so far? The effects of microgravity are different for everyone. For example, a sumo wrestler's feet need to provide 1,825 newtons of force to prevent his 186 kilogram body from cracking his legs. In space, this sumo has no normal force acting on him. As a result of the little normal force needed to keep the sumo upright, muscles and bones degenerate. Space weight loss may sound good to a dieter, but this loss will not be done through burning fat. The sumo can expect his muscles to atrophy at a rate of 1.5% while his leg bones weaken by 10%. Although you lose muscle and ultimately become skinny, you will be glad to know that your legs and vertebrae separate, curing your backaches and making you about 7 centimeters taller, so you can finally stop cheating when you measure your own height. Is there a way around this problem? Scientists are finding new ways to stop the harmful physiological effects of microgravity. So far, rotation and linear acceleration are the best ideas to mimic the force of gravity on space vessels. Rotation relies on the body's inertia and the centripetal force created by the outside wall of ring-shaped, uniformly rotating ships to simulate the effects of gravity on Earth. For enough force to be felt, the ring would have to be 224 meters in radius. Like the idea of an accelerating car, the linear acceleration of a vessel and the inertia of its passengers' bodies would push the passengers backwards into the vessel walls, giving them the sensation of gravity. No matter how you spin in it, you must appreciate how gravity is present in our everyday lives, keeping our muscles and bones strong, not just bringing you down.